eastern end of it. Okay? So what we do also affects the coast quite a lot. When we build walls like this, we reduce sediment supply. How the beach works is the material behind the beach is the natural feeder to absorb that energy when we have storm events. We cut out that absorption, we cut out that ability to feed itself. It's got to feed itself from somewhere else. It feeds from the ends, and this is what we classically call end effects of those sorts of things. And we have things like what we do in Christchurch. We knock down our sand dunes at various places along Brighton. We knock them down because we think that increases our recreational use, increases our views, but it also increases our risk. We've reduced our buffer. We change the vegetation. Right, and here in Christchurch you can see the vegetation here is marrons and ice plants, both introduced plant species, but that has totally changed the morphology of our coastline, what height those dunes can grow to, what slopes they might be at, what their vulnerability to wave attack is. Because all of those plant species have different ability to trap sand, different ability to resist salt. So the things that we do also affect the level of risk quite dramatically. And some of the things we do to reduce risk in one place increases risk somewhere else. And then we've got the other sorts of hazards. Seawater inundation, made up of tides, astronomical tides. Tides vary from place to place, and they vary from time. The tides here in Christchurch are quite different from what they are in Tasman, for example. Tasman has the largest tidal range in New Zealand, something like a tidal range of 4.6 metres from a mean high water spring to a mean low water spring. So if we went 6 hours different in our visit to the coast, the water level would be almost 5 metres different. Huge amount of then change in hazard, depending on the time of arrival of the storm. Maximum tides can be up to about 0.3 of a metre above those mean high water springs, and you will see, quite often you see the literature, mean high water spring is this, right? That doesn't mean that's the highest the tide can ever be. Astronomical tides due to gravitational pull of the sun and the moon can be up to 0.3 of a metre above that. That's just the mean of the ones over 18.6 years, all right? So it's not the highest that we'll ever have. So we can have then, if we looked at our Tasman example, we can have water levels up to 2.5 metres above this thing called mean sea level. So the height, all our land elevations in New Zealand are in reference to mean sea level. So if we had an elevation of 3 metres, for example, you go, oh yeah, that's 3 metres, that's pretty of elevation. Now that's 3 metres above the mean level of the sea. If we were sitting in Tasman, 2.5 of that can be taken out by tide straight away, without any other effect. And so heights can be deceptive. And that becomes important when we talk about tsunami heights and things like that. Then we have storm surge. Storm surge is the super elevation of the seawater level due to meteorological conditions. So it adds to the tide. Two components of storm surge, one being low air pressure, the inverse barometer effect. When water level rises, sea level rises due to the reduced air pressure. And it rises by 1 centimetre for every millibar that we go below 1013. So if we had a weather system, a low pressure system of 960 millibars, which is possible for us travelling through Bobo Strait and coming up the east coast of the South Island, we would have a sea level of 0.5 metre above whatever the tide was. So in Canterbury our tidal range is around 2 metres, so our mean high water spring is 1 metre above mean sea level. We can add another 0.5 metre onto that just by a barometric effect, quite easily. On top of that we have what's called wind stress, where high onshore winds pile water up against the shore. So the wind comes in, it gets trapped in against the shore, and it adds to the water level. We can add another 0.3 of a metre to it. So our tides, by the combination of IB effect and wind stress, can add 0.8 to tide. So don't just ever assume that the tide is the maximum of the water level you'll have. We can easily have 0.8. Our 1 in 100 year storm surge is often put at 1 metre. And they're quite small internationally. Things associated with Hurricane Katrina, storm surge was around 8 metres. So we had tide, then 8 metres, that's not waves, that's 8 metres of water increased because of IB and wind stress. And remember, those things aren't like a wave, they don't last 5 to 10 seconds, they last for the hours. So it increases the level of risk considerably. Tsunami we're going to talk about in a couple of days' time, and you're going to tell me all about what you know about tsunamis, and that should fill most of the time. River mouth closure. It has two levels of risk, I guess. One is when we close our river mouths in small, well not so small, say medium-sized rivers in New Zealand and in Canterbury in particular, close quite regularly. Things the size of the Ashburton, the Opahis, the Oraris, getting up towards the Rangatatas, all right, can close, and they're quite large river systems. That causes a problem with backwater effects. So when the mouth is closed, we get a flood or a fresh coming down the river, it can't get out, we get flooding of the low coastal hinterland. It also is a hazard because of the loss of recreational fishing. All of those Canterbury rivers, highly valued salmon fisheries. Of course, when they're closed, you can't fish them. Loss of tourist dollar, loss of recreational opportunity. It is a hazard. Sand dune blowout and migration usually occurs where we've removed the vegetation. We decided that the native penaos and spinifexes, if we were a little further north, weren't doing a good job. We really wanted to get rid of them. In a lot of cases, the penao was eaten. It was palatable to sheep and particularly to rabbits. So it was removed. We then ended up with major problems of sand blow. Sand going over more productive pasture. There was a major problem in the Manawatu, major problem in Christchurch in North Canterbury. And that's why we have marron grass now, the predominant plant along most of our coastline. It was an introduced plant around the 1900s to stop sand blow effects. Right? All of the marron in Christchurch was introduced around that period to stop sand blow effects going through the suburbs of New Brighton, Parklands, Waimara. And then we come to the last hazard, the one that I put a question mark on, is sea level rise. I put a question mark on it because the question is it a hazard? Sea goes up and down twice every day. Why, if we were sitting in Tasman, 4.5 metres. That's not actually a hazard. So sea level rise, what we're really talking about is the accelerated rising of sea level due to climate change, due to the warming. Okay? Is it a hazard on its own, or is it just an intensification of all the other hazards that we already have on the coast, is the question. And what about the other climate change effects on coastal hazard drivers? Because if we are also changing sea level rise, the scenarios say that wave approach can also change. If we vary our mean wave approach by 1 to 5 degrees, on all those little bayhead beaches, we will change their shapes. So places that are stable now will become erosionary later without sea level rise. And one of the scenarios of climate change is more westerlies. It means more storminess because we get more southeast storms in the South Island. That's without climate change, without sea level rise. What about sediment supply? It's the scenarios of climate change as well as being drier in some places, that we have more intense and more frequent storms in our up catchments. What they do is deliver sediment to our coast. So we might have a feedback mechanism where in some places our coastal erosion components go down, and that the increased sediment supply can compensate for any sea level rise effects. Because where coastlines are is a balance between those two components. So I don't think we should ever just get totally trapped into thinking about sea level rise on its own. We should think about climate change in total and what it does with sea level rise, wave approach, storminess, frequency of storms, duration of storms, and sediment supply. Unfortunately, we don't. We get sucked in by the media about sea level rise. So what is it about sea level rise? This is the sea level rise graph for New Zealand over 100 years up to the early 2000s. It's probably about 5 years old now. And we can see it's been steadily rising. All right? Well, not steadily, it's been jumping around in various intervals. The top line is the line from the ports of Auckland. Okay? And we can see that it varies. The average is 1.7 millimetres per year. And that's around about the global average as well. That's around about what global sea level has been doing. Okay? But we've had periods of more rapid rise and periods of almost static. And so the bottom graph then relates that to the SOI, the Southern Oscillation Index, which is our index of whether we're in La Nina or El Nino. All right? El Nino being those that have a negative index, La Nina being those that have a positive index. And at the top we've got the phases of the IPO, the specific oscillation that's going on. And we see we have high rates of rise when we combine La Nina with negative IPO phases. When we went through into the 80s, we were largely in El Nino conditions, largely in positive phase, so our sea level rise was quite low. We switched into the 2000s and we were starting to get some rise effects. Okay. Unfortunately, all our records, while our records of imports and things go back 100 odd years, they really were for shipping, so they're not that precise in terms of taking out sea level rise effects. So these things aren't hugely precise. But all our records of change of shoreline from beach profiles and things like that really only started about here. So they're all in this sort of phase. So how well do we know about how our shorelines respond to sea level rise or sea level change? Okay. The future with sea level rise is something like this. So here's our ports of Auckland that we saw last time. Here's our 1.7 mils. Here's our projections. And we can see why it is such a potential risk for us. It's because those projections just escalate up. And in fact, IPCC in 2007 have reviewed these predictions, and the most likely range now, the middle of that most likely range is up around 0.59 metres a year in the next 100 years, possibly up to 0.9 metres a year. Okay? So this is why we are really interested in sea level rise. But we're not particularly sure what effect it will have on our coast. To give you some idea why it's a problem, here is Wellington, Queen's, the water level charts and probability of exceedance, so a risk curve if you like, for the Queen's Wharf in Wellington. So with no sea level rise, we might have high water above what our base was. The risk of it being 0.9 metres above is very, very low, 10 to the minus 5. And the probability of that is quite low. We have a 0.2 metre sea level rise, which is what's predicted by 2050, right? Suddenly, that probability, that same probability, it's a lot higher, it's a 1.1. So the 0.9, now if we come across, the probability of that is 1 in 10 years. So our what was 1 in a 1,000-year storm now becomes, something like, 1 in a 100-year storm. So flooding associated with high tides combined with waves and things suddenly went from 1 in a 1,000-year probability to 1 in a 100-year probability. If we go in the next 100 years, that 1 in a 1,000 or 1 in 10,000 year probability suddenly becomes a 1 in 1 year probability. So the things that we built Te Papa for, if we didn't account for sea level rise, we said, yep, it's never going to get flooded in a 1 in 1,000 year sea level, suddenly occurs in 100 years' time, which we want Te Papa to last for, every year. Right? So the risks escalate considerably with a quite small change in sea level. That's why we're interested in sea level rise, because it changes our risk factors considerably when we put assets in place. And that's what we have to do because we don't have a lot of other places to put it. Right? Sea level rise is not just about flooding. Oops, we won't worry about that. It also affects shoreline stability. Erosion occurs because what beaches try and do is get back to an equilibrium cross-shore profile shape with that new water depth. So in simple terms, what it does is the water level goes up. What it says is, gee, I've got more water depth under the sea, close to the shore. To get back into equilibrium, I'm going to take some material off the shore and put it in there to get back to that depth. So it gets back to equilibrium. So we have erosion of our shorelines, as long as the shorelines can erode. And sand beaches particularly can erode. So the volume eroded from the beach is equivalent to the volume required to re-establish that equilibrium nearshore profile. Well, this is the theory. Okay? And so it is dependent then on the nearshore wave climate, on the ability to move material, which is termed dependent on the water depth, because higher wave, we get higher waves with more depth. So places which have high wave climates,